Hello, everyone, and welcome to today's webinar on understanding and improving the performance, durability, and reliability of electric vehicles. Our presenter today is Andrew Halfpenny. Andrew heads technology and innovation for HBK's nCode product brand. He holds a PhD in mechanical engineering and a master's degree in civil and structural engineering. Over the years, he has introduced many new technologies to the automotive, aerospace, and power generation sectors. These include customer usage monitoring, target customer analysis, proving ground correlation, accelerated laboratory testing, and mathematical simulation. His most recent work has been developing methods to measure and improve the performance, durability, and reliability of electric vehicles. Andrew is a founding member of the NAFEMS Professional Simulation Engineer Certification Scheme and sits on the Committee for Dynamic Testing. He is also a visiting lecturer on structural dynamics and structural health monitoring with the University of Sheffield. Andrew, it's all yours.
Thanks. Thank you. I hope you enjoy this presentation. I'm going to be talking about understanding and improving the performance and durability and reliability of electric vehicles. But a lot of what I'm going to be talking about here is very battery specific, so it will apply to other industries too, even though it's electric vehicles that I'm dealing with predominantly. And over the next few weeks, we've got 9 seminars in total talking about battery measurement and improvements. And this is the first. So hopefully in this one, I'll just introduce you to the next 3 in particular, but then the ones after that too. So for me, this story all started about just over 3 years ago now, when my boss asked me, he said, lots of people are using our software for designing electric vehicles. So I'd like you to go out and have a chat with them and find out, what are they doing today? What are their challenges? And how might we help them with those? So really, ever since then, I've been having cups of coffee virtually in the last year and talking to people about the challenges with electric vehicles and battery technology, really. And I suppose they fit into these 3 areas. There's mechanical and durability aspects, there's the performance and efficiency aspects, and there's also the reliability aspects too. So over today and the next 3 webinars, I want to go into these in more detail for you. But first of all, let's not go through this. Let's just pull them apart and just have a quick look at what we'll be looking at. So first of all, when we think about a battery, we tend to think about this little C cell here, don't we? The one on the left there. And sure, that is a battery, but it's actually a single cell. What we actually do in a vehicle battery is we join these together to create a pack. And that's what's storing our energy for our vehicle or whatever we're using it for. Now, they don't have to be C cells, these cylindrical cells. There are also laminated foil pouch cells, and there's also the prismatic hard case cell as well. So that very much depends on what your design of battery is going to be. And the industry's still out on which performs best. There are benefits and advantages and disadvantages of each at the moment. So we're looking at all of those. Now, each of those single cells gets joined together. So in this case, we call this a module, and these cells are joined together both in series and in parallel, and they create usually around about 60 volts. So that's the maximum we can go up to with the hazardous voltage restriction. So they tend to be around 60 volts maximum, and then we join those modules together in series to create our battery pack. So where are the structural aspects with this? Well, first of all, if we look at this cylindrical cell, then we actually notice that it's supported structurally between these bus bars. These convey both the electrical current and they also structurally support it too. So we've got this fairly heavy mass that's between a flexible structure, and it's bouncing up and down as it's going over the road, and it's got all the other vibrations. And that starts to cause fatigue at the joints in here. So one of the main failure modes that we're seeing in this type of structure is a vibrothermal fatigue effect. So it's vibro because the whole thing's vibrating at a whole range of frequencies, and it's thermal because there's quite an extreme thermal expansion in there as well. So we get that constrained thermal expansion coming in too. Now, when one of these joints fail, it doesn't mean it's the end of life for the battery. No, the battery will still carry on. But what it does mean is that that cell will no longer be contributing to the charge of that battery. So we're getting this progressive degradation over time, not an electrochemical degradation in this case, which we're probably all familiar with, but a structural degradation. So we're interested in trying to improve the efficiency of the batteries and the structural durability in order that we can get much longer life from them. Now, our challenge here is we've got a broad range of frequencies going in from the very low road load data to the higher things such as torque ripple effects and things like that my colleague Mitch Marks likes to talk about. So we've got a broad range of excitation, and also we've got a broad range within our battery structure of resonances too. And we've got a highly variable damping, which changes with temperature. So again, we need to start to look at that and see how we can use that damping to take out some of that energy. Now, in addition to this, I'll also be talking about structural fatigue, because in an electric vehicle, we want to use those batteries to transfer structural loads. They're part of the chassis now. We also want to use them for crash protection too. And internally, we've not only got metallic joints, but we may have adhesive joints and hybrid joints. So again, I want to have to talk about how we start to do that. And in general, for all of our lightweight vehicles, how do we go about improving the structural light weighting of them to get more efficiency and therefore more range? So with this webinar, this will be on the 24th of June. It'll only be sort of 20 minutes like this one, but what we want to cover here is the battery as a mechanical structure. We're going to look at fatigue design of the battery packs, try and characterize that vibrothermal fatigue on the batteries. Also, derive accelerated vibration tests, which better characterize the way that vehicles are used on the road. And again, look at vehicle light weighting and jointing in particular. So hopefully after this, we'll get a much better idea of how we can reduce battery degradation, understand the vibration and thermal loads on the battery, understand the chassis and structural loads, as the structural battery is now part of the chassis, and get more representative vibration tests, which one of my colleagues will then talk about later, and a lighter, more durable battery structure. Now, another presentation I want to do is also on battery performance and efficiency. So if we think that an electric vehicle is actually, it's got energy stored in different stages, and it transfers them backwards and forwards all the time. And with each transfer of energy, then we end up with an efficiency loss. And if we can measure that and we can characterize it, it means that we can work to reduce that loss and therefore get better efficiency. So for me, our story starts with a wonderful piece of hardware that HBK produced called the eDrive system. And what the eDrive system does is it allows us to measure torque and power and energy in all different various ways very, very quickly. So typical output is things like this. On the AC side, you can see here I've got an AC current. Here we can see it's not a sinusoidal here, it's a pulse width modulated output from the digital inverter that we're seeing here. And what that's creating is not sinusoidal at all. That's really quite peaky, and that gives us a power curve down here. Now eDrive is really quick, and it can calculate on the fly the active, reactive, and apparent power coming out of that. And it can do that right down to the half rotational cycle resolution. Now, eDrive will also log those data for us, and that means that we can now analyze that even more in offline software. So by using nCode GlyphWorks, for instance, we can take that log signal, and because we're no longer worried about real time, we can do far more accurate analyses on those data. And actually, in the next version of GlyphWorks that's coming out in about 2 months' time, there's the first new glyph for power analysis coming out in that. And what this allows us to do is go beyond this half cycle resolution. So we can now start to look at the power factors at the inverter frequencies themselves. What's more, we don't have to assume that they're sinusoidal, because they're clearly not. So we've got methods that can analyze non-sinusoidal data. It doesn't have to be 3-phase. It can be any number of phases, so it can handle that. And most importantly for electric vehicles, the whole thing can be transient as well, because it's not steady state like you would have on a power line. And the other thing I want to talk about as well is this bit here, this kinetic energy. Because again, in GlyphWorks, we can take GPS data and calculate with some accuracy, really, to within about 5%, what the power requirements are of a vehicle. And this is really good, not just for looking at efficiency, but also for looking at what people do with vehicles in order to better understand real customer usage. So this is on June the 29th. It's a big day, that is, because it's my birthday too. And in this webinar, we're going to consider the electric motor efficiency and the loss mapping. We're going to be looking at the power measurements. In particular, we're going to concentrate on the digital inverter output and the electric motor, because that's where we can make lots of changes to improve efficiency. And we'll also be looking at that real-world battery usage and target customer analysis too. So hopefully after this, we'll be able to achieve a better range on our battery, a better accuracy from all the analysis, and a much better understanding of how real customers are using vehicles throughout the world. And then finally, my last webinar, I want to be talking then about battery reliability. So, when we innovate, when cars were first made, the holy grail of a car is that you have 100% reliability until the design failure date, and then everything fails all at once on the road. And this picture came from a statement to that effect that Henry Ford once made. He wanted to see every part fail simultaneously at the end of a perfectly reliable period. Now, we know that that can't really happen with a car, even though we try very hard. Bits fail at different times, and they follow this probability distribution of that. And sometimes they have a wide distribution, so you get a lot failing earlier. Sometimes we try and make it nice and tight so we can control it. The other thing, though, that we get is that some of the parts, when they do fail, are replaceable. So we can come up with maintenance schedules and things like that. So with the maintenance schedule, for instance, we can start to see by how people drive, can we detect when parts are failing? So one of the things we want to look at is obviously to make sure that variability in strength, that the variability in users doesn't overlap, because where they overlap, we get failures. So we want to control that. But we also want to have a look at parts which wear and we can observe them. So, for example, on a car, some bits wear and they show signs of that wear. We know that we replace tyres when the depth of the tread gets to about 2 millimetres, because after that they're going to wear out quickly and they're not very effective. We know that we change the wiper blades when they start to split, because they don't clear the rain up anymore. We know that we're going to replace the brakes when there's still just a little bit of padding still on them, and we'll change the discs, because we know that they won't make it safely through to the next service interval without going down to the studs. All of these are what we really call today a condition-based maintenance, or an on-condition maintenance. We replace these items when we observe that they're wearing out. Of course, not all items can do that. Some battery items can, though. So things like if we're looking at the thermal management of batteries and we find that there's a problem there, we can usually detect that and we can swap it and replace it. So there are some battery items which obey this, but most of them don't. So with those, what we tend to find is historically, we use maintenance databases. So back to our car analogy, if you're looking at things like spark plugs, you won't usually wait for the spark plug to fail before you replace it. You'll replace it when it's getting towards its end of observed life. And the cam belt and things like that in your car, you won't wait until it fails, because that's likely to ruin your engine. So we'll replace it at around about 30,000 miles or 50,000 kilometers or whatever, in order that we never get into that failure mode here. And this is really the birth, if you like, of what today we call reliability-centered maintenance. So from our historic data, we can create a failure rate curve, and it's got some scattering. And what we do is we look at an aging metric. So this could be in cars, it's usually road miles and calendar age. And based on one of those metrics, we can decide we retire components early. Now, that's been serving us very well ever since the car was invented, really. But how do we do that with battery technology when it's still relatively new? We don't have that huge maintenance database to rely on. So in this case, we don't want to be producing cars and inadvertently having a huge reliability or maintenance overhead that we don't know about. So in this case, we're going to start to look at reliability testing. So how do we test things in order to estimate what the failure rate is going to be? So this curve here, for example, is a good illustration. It's saying that the warranty age of our vehicle here, 8 years, I would anticipate 20% failures. That means that 20% of those batteries would be replaced on our dollar under maintenance. It also means that we can look down and see, well, what contributes most to that? And is there a way that we can prolong this and get a better life and get better reliability? So we're going to talk about that in greater detail in that particular seminar. Now, that's very good when we're talking about today, but we all know that we live in a data-driven world, and we're getting more and more data from cars all the time. And this is allowing us to build up a usage database as well. And this data is going to grow. So now we've got the maintenance, we've got the health data, but we've also got the usage data. Is there a way we can combine those data together to help us? So in this case, we look again at analysis techniques, so physics-based engineering and data-driven machine learning. And I'll start to just introduce the concept of a digital twin. Now, that's one of them buzzwords, isn't it, which everybody's heard of and everybody's got a different definition of. So as well as that, I'll give you what my definition of a digital twin is, so that it's not just a fantasy, but it's something we can actually start to do. So this particular webinar, this will be on July the 1st, again, just 20 minutes. And we're going to look at battery life analysis. We're going to look at battery performance, degradation and modeling. We're going to have a look at that digital twin. But one thing that I think you'll be really impressed about is the FMEA, failure modes and effects analysis. This is a really good way of, with virtually no experience at all, of working out how you can make batteries more reliable. And also it's a knowledge-based system, so that that knowledge will exist within the company and therefore we'll get better from it. So the benefits for this one, reduce our risk, reduce our warranty exposure. We want to start to model and reduce that battery degradation, and also talk about using FMEA to build a better brand image and to also store that corporate knowledge. So I'm going to do the next 3 webinars here, and then after that, I'm going to hand over to my colleagues. Now, I'm interested in analysis and turning data into insightful information to make decisions, both design decisions as well as maintenance type decisions and reliability. But to do that, I need data. And those data typically come from tests. And when we talk about tests, a lot of people think of the qualification tests. In the vehicle industry, we tend to think we want to reduce the number of tests. But those are what we call qualification. These are tests to confirm that our analysis is right. Actually, though, we need another set of tests too. We need what we call parametric tests. And these tests give us the information to do the analysis so that hopefully when we qualify it, we're right. And more and more today, we've also got service data coming in as well. Now, we rely then on these 2 sets of tests in order to make sure that we've got the right data in the model to do the analysis, and the model is getting the right answers so that we don't put ourselves at risk commercially when we release a new vehicle. So to get the best quality of data then, my colleagues are going to talk, first of all, on the 6th of July. My colleague is going to talk there about actually doing that physical test, looking at the battery structural durability and design testing, getting the best data we can from that. And then also on July the 8th, looking at short circuit testing of these high performance batteries. Of course, the parametric testing is really important to us as well. So on July the 13th, we're going to be looking at the physical testing of a single cell. So this is the pressure analysis testing that we're getting here. And then one of my favourite ones on July the 20th, we're going to be looking at vibration testing of live batteries during the charge-discharge cycle. And then finally, the last one, we're going to be looking at physical testing again. And this is all about battery performance and thermal integrity on July the 27th. So I hope actually in this little trailer, 20 minutes that I've given you some enthusiasm, told you about what we want to talk about. And I hope that you'll join us for a coffee break and come and listen to what we've got to say. And hopefully together we'll learn a little bit more about battery technology in general, not just electric vehicles.